Recording.
Okay.
Okay, so we will continue with the second speaker today. We have the honor and pleasure to have with us Professor Arick Shao from Cambridge University in London, in the United Kingdom. We can say that he obtained his Bachelor of Science in Mathematics from the University of Texas, Austin, and the PhD from the Princeton University, under the supervision of Sir Hugh Kleinerman. Then he obtained postdoctoral and research positions in the University of Toronto in Canada and the Imperial College London. And since 2016, he works as a professor and researcher at the Cambridge University of London. We can say also that his research interests include partial differential equations, such as hyperbolic and wave equations, dispersive equations, and geometric PDEs, analysis and geometry, differential geometry, functional analysis, and harmonic analysis, and mathematical general relativity, such as Einstein equations or Lorentzian geometry. So thank you very much, Arick, for having accepted our invitation to give this talk and sharing your knowledge with us. All yours.
Okay. Well,
Yeah.
thank you very much for the first of all, for the invitation and also for the very detailed introduction. Yeah. So today, I guess I'm taking a bit of a break from control theory and talking about something I've been working on recently on I guess, scattering and asymptotics for kind of these uh, systems, which I'll kind of say more about soon. But let me first mention that everything here is joint work with Boris Sabikbek, who is currently a postdoc at Ghent University. With Michael Ruzhansky. Okay, so maybe I'll just start with a quick introduction, kind of what are we doing, right? And so what kind of PDEs are we going to study? So we're essentially going to look at first order linear hyperbolic systems, but not just the usual ones. We want to look at systems that become weakly or rather degenerate hyperbolic as the time goes to say 0. And then we'll also want to look at systems that have what are called critically singular coefficients as t goes to 0. And I'll say a lot more about what exactly that means in the upcoming slides. But here, let me just say a bit about the kinds of questions that we want to answer. Right. So first, the first goal is that we want to be very general. We want to treat a very general class of such systems. Right. And then as far as the questions, the first one is asymptotics, right? So if you start with some data at some positive time, then you want to find out, what the limiting behavior is for these systems as t goes to 0. And then you also want to prove, say, the converse of this, right? So say if I were to give you a bit of a appropriate asymptotic data at t equals 0, then can you solve the equations forward? And then one kind of feature of these systems is that you actually lose regularity at t equals 0. And so we want to basically understand why and also give a precise quantification of this regularity loss at t equals 0. Okay, and one other question before we kind of get into details is just why would you want to study these equations, right? And so one reason is that this kind of degenerate / singular phenomena are found in many PDEs of interest, right? And these can be something abstract like singular wave equations, but also wave or Einstein equations on Big Bang singularities and also in some equations in fluid dynamics, right? And so that gives a bit of motivation for kind of understanding what's going on here. Okay, and then kind of the eventual kind of goal of all this research is to be able to study, say, nonlinear, quasi-linear hyperbolic systems, right? And so if you want to kind of study these kinds of systems, then the first step that you need is a robust linear theory that can treat, a whole large family of operators. And that's kind of why we want to kind of do things with a certain level of generality. And then what makes this hard, right? And so one quick way of explaining this difficulty is that there is a certain level of, say, criticality in the degeneracies of the system, and actually this leads to some precise behaviors that are actually not quite well understood, and because of this criticality, then we'll have to look at a system in exactly the right way if we want to kind of pick out the precise information that we need. Okay, so now if I were to go directly into the main theorem and for the abstract systems, then you'll all be very upset with me because it's kind of very abstract and it's very hard to make sense of. And so, well, the idea is to first kind of build some motivation for this by looking at some model equations. So hopefully we get a sense of what's going on and why it's going on. Okay, so I'll go into some historical results that kind of motivated this whole kind of a direction. But before I do, just any questions so far? Okay. Okay. Well, if not, let's just get into kind of a very simple wave equation. So this is just a wave equation in one spatial dimension. This looks like the usual thing you would study in your undergraduate class, except that in front of this dx squared term, you have this extra factor t to the 2l. And here we can think of L as just some natural number. And so then this equation is what's called weakly or degenerate hyperbolic. And that just means that, well, if you look at the characteristic speeds of the system, it's plus or minus t to the L. And then these two speeds become the same as t equals 0. Right? And this leads to a phenomenon called weak hyperbolicity, meaning that if you try to diagonalize, if you write this as a first order system and you try to diagonalize the system, then it becomes non-diagonalizable at t equals 0. Okay, so that's fine, but then I also left some space here for other lower order terms. And so kind of what's known about these weakly hyperbolic wave equations is that if you add certain lower order terms to this equation, then you can actually lose regularity at t equals 0. Right? And there's this very long history of people studying this, right? So these are things with kind of perfectly smooth coefficients, but you still lose regularity at t equals 0. And there's been various works of, say, Levy and so on, who kind of try to quantify or at least come up with conditions that tell you when you lose regularity and how much regularity you may lose. Okay, but just to kind of skip some of the history, let's just go directly to a certain low order term here. So we'll just add, it's basically dx phi, and then this constant times t to the L minus 1. Right, and so long story short, what happens is that if this coefficient, this thing in orange, goes to 0 too quickly, then this becomes a perturbative term and there's no derivative loss. Right? And so then this equation just becomes well posed in HS spaces, just like the usual wave equation. And now if this orange part goes to 0 too slowly, then you actually have infinite derivative loss. And then in this case, you can only have well-posedness in certain Gevrey spaces. Okay. But then what's most interesting is if you have something that's exactly in between the too fast and the too slowly, which is exactly this power L to the L minus 1. And so one can think of this as the critical rate. And then in this case, you'll actually lose a finite number of Sobolev derivatives. Okay, and kind of one way to kind of try to see why this may happen is, well, we can look at some very explicit solutions. And so here, let's just take the specific case when L is 1, and then this constant C is just 4k plus 1. Right, and so then we have this exact wave equation here. And then for the initial data, we just have anything we want for phi, and then dt phi is initially 0. And then what's nice about this particular equation is that you can write the solution of this equation explicitly, and it's actually given by this series here, right? In particular, if I want to write phi at time t and x, then it's actually written as a sum of derivatives of the initial data up to k, and then this c are just some explicit constants that you can compute. Right, and so then what this tells you is that there's this unavoidable loss of k derivatives as you go from t equals 0 to t positive. And by taking k to be as large as you want in the equation, you'll lose as many derivatives as you want as well. Okay. And there's one more explicit example now in Fourier space. So this is found in various papers and also not that hard to compute on your own. But here we now take an arbitrary L. And then for this constant C here, we take that to be exactly L. And what's nice about this equation is that you can write the solution explicitly in Fourier space. And it looks like this. And so here we have arbitrary data for both phi and dt phi. Right, and so then if I were to take the Fourier transform of phi at time t, then I can write this in terms of the initial data by this equation that I have here, right? And in particular, right, so I have just phi hat on the left-hand side and then phi 1 hat on the right-hand side. And so there's already a loss of one derivative there, right? But usually if I have the usual wave equation, then this integral that you would get here would give you something like sine of xi over xi, right? And so you gain that derivative back. Okay, but here, because now you have this t to this power, then you have this a bit of a stationary phase in this exponential term, and you can either compute this explicitly or using Randall-Corbett lemma or whatever you want. Then you'll see that this integral here behaves like xi to this minus 1 over L plus 1. And so since you've lost one derivative and you gained 1 over L plus 1 back, then what you see is that for this equation here, you lose a fractional L over L plus 1 derivatives as you go from t equals 0 to t positive. Okay, so now we can be a bit more general, and now we can take an arbitrary L and, as well as an arbitrary C, right, and an arbitrary initial data as well, right? And so now we don't quite have explicit solutions, but you have kind of the next best thing, which is that you can write the solution explicitly in terms of confluent hypergeometric functions. These are kind of very classical analysis things. Right, and so it's basically you have two confluent hypergeometric functions, f11, and then the parameter that goes in is w, where w is just xi times this power of t to the L plus 1. Okay. All right, so that's the solution. And so then what you know, if you know anything about confluent hypergeometric functions, right, is that, well, it satisfies an ODE, and that ODE has singular points at 0 and at infinity, right? And so since you have this regular singular point at w equals 0, that means that our solution here will behave like some power of w, right? And had some power of xi near w equals 0, and then it'll behave like some other power of w near w equals infinity. And since w contains powers of xi, then that is exactly what gives you this this loss or change of regularity, right? It's these extra powers of w. Okay. And if you're careful enough with these computations, then you can actually sit down and you can see exactly what it is, right? So the first equation here is that if you start, we start from time t and you solve backwards to time 0, then instead of getting just hs and hs minus 1 on both sides, you get something strange looking on the right-hand side. And then similarly, you can also start with data at t equals 0 and then go forward to time t, and you get, again, some kind of regularity shifted energy estimates as well, right? And you don't have to know the exact figures. That's just happens to be what you get for this problem. Okay. Okay, so this comes from explicit solutions and just properties of the hypergeometric function. But that's a bit too specific. And so then one kind of question that one can ask is, what about more general, say, degenerate wave equations, right? And so now, instead of having just constants in front of these powers of t, we replace these constants by, say, nice smooth functions, right? And then we can also have a dt to a phi term and then a phi term as well, right? And just to make things general. Right, and so, of course, for these kinds of equations, you no longer have explicit solutions in terms of hypergeometric functions, so you need some kind of softer methods in order to derive these properties. Okay. And one can ask the same question in higher dimensions as well. So it looks pretty much the same, and one can see later on that we can get pretty much the same kinds of results for higher dimensions as you can in 1D. Okay. And so now there are many results over the years for kind of both these questions, right? And so, for example, using kind of classical physical space arguments, integrations by parts, energy estimates, and so on, right? So then you can actually treat these equations with having very specific, very general coefficients that even depend on x, right? But the downside of using physical space methods is that you can generally only kind of capture integer or non-fractionals or non-fractional derivative losses, so you don't tend to get the optimal results here. Now, on the other hand, I think in the early 2000s, people have used kind of Fourier/microlocal type results And there, I think it's much more difficult to treat coefficients that depend on x. But on the other hand, you can get very precise derivative losses, right? That we want to get in this talk here, right? And so, because of this, kind of what's coming up will primarily be based on these Fourier plus microlocal methods. And so just to kind of summarize all these previous results into a theorem, then what you get is that for this wave equation, same one that I had before, here I just wrote this in 1D, the loss of regularity depends on certain parameters, basically this exponent L, as well as the values of A, B, and C at t equals 0. And then the amount that you lose, just like before, can be explicitly computed in terms of these quantities. I won't write the formulas here. And then, but there's also similar results in higher dimensions too. Okay, and one quick remark here is that this loss of regularity, even though it depends on L, A, B, and C, it doesn't depend on the remaining coefficients G and H, right? And that's just because these terms here are not critically singular enough to kind of change the regularity. They're the perturbative terms. And so then the question is, what is a mechanism for regularity loss in these kinds of equations, right? And so next thing we'll have to do is to try to explain some of the main ideas behind the proof of this theorem, and also hopefully try to communicate kind of why this is hard to prove. And since we don't have that much time, right, basically we don't want to kind of do two things at once, and so I don't just want to give the ideas behind the proof of the existing theorem, but to also kind of look at a newer class of equations, and also kind of along with that, also talk about the ideas behind some newer results as well, right, that are new to this talk. Okay. Okay, so before I go into that, let me just pause very quickly to see if anyone has any questions so far. Also to make sure that I'm still connected to the internet. Okay, all good so far. All right, so moving on. Okay, so now let's look at this larger class of critical degenerate singular wave equations. And just to kind of make the slides a bit easier, let's restrict now to just 1D. And there's kind of two new things that are going on. So here in the exponent L, here I don't have to take a natural number. I can take basically anything that's bigger than -1. Any real number bigger than -1. And then the other thing is, in these kind of two coefficients that were safe before, right, I want to also add a singular weight, t to the -1 and t to the -2 here, right? And that just has the effect of making these terms singular enough that it's going to and have the same effect as this previous term with C. Okay. And let's, again, just to simplify our slides even more, let's also set B here, this cross term B to be 0, and then this potential term H to be 0 as well. Okay, it just makes the equation a bit simpler, but it doesn't kind of it doesn't take away any of the main ideas. And so then, with that in mind, let's also take a spatial Fourier transform in X, and then you get this equation here in pink, right? And that's the equation we'll be kind of studying in the kind of upcoming bit, where we try to understand the main ideas for this model problem. Okay, so the starting point here is to recall from the previous section when we talked about explicit solutions for the model equations, right? Then those were given in terms of this quantity W, which is like C times T to this power. Right? And then these explicit solutions were given in terms of this confluent hypergeometric function, which had singular structure at both W equals 0 and infinity. And so the first key idea that I want to get across is that the singular nature at both W equals 0 and W equals infinity that still persists here in this more general problem. Okay? And so the first thing we have to do is to kind of capture this singular structure, right? And so the way we do this is we define kind of z or z here to be t times this 1 over L plus 1 power of c as a rescale time, right? And so this is just w from before to the 1 over L plus 1 power. I think it's just more convenient to work with something that's the same scaling as t. Okay? And so the idea is that, using this z here, we want to isolate the behaviors near z equals 0 and z equals infinity. Okay? And so the way that we do this is we want to split our time frequency space into microlocal zones. And this is kind of an idea that goes all the way back to around 2000 or so, right? And so basically, we have this region ZP here called the pseudo-differential zone, and this is just the region where z is small. And then you also have what's called the hyperbolic zone where z is big, and then intermediate zone is this region in between where z is close to 1, and that we won't worry about because the analysis will be trivial there. But hopefully this is just a quick drawing of what the time frequency space looks like. And hopefully, normally I would draw this on the board, but hopefully people can remember what that looks like. Okay, and so then the idea is that we now want to write our wave equation as suitable first order systems. And so the first kind of tricky thing is that we want to write them using different unknowns in the pseudo-differential zone when z is small and on the hyperbolic zone when z is large. Okay. And so first in the pseudo-differential zone, you have basically you have 1 over t times phi hat and a dt of phi hat as your unknowns. And then what you get is you have this 1 over t term here, this Fuchsian term, and then you have kind of these extra terms in gray that I'm not writing that are nice. And then for large z, you still have dt of phi as your as one of your unknowns, but the other one you're taking, say, I and then times t to L times xi times phi instead. And then if you write the equation in terms of these unknowns, then you have first of all this part in orange, which essentially gives you the hyperbolicity of your system. And then you have a Fuchsian term as well, this 1 over t term. And then what's remaining will be kind of nice perturbative terms that we don't have to worry about so much. Okay. And so then the next kind of big idea is that we want to kind of put everything in the right scaling so that it has a good structure. And so the right scaling is in fact given by this frequency rescale time z we had before. Okay. And the observation is that if you write these first order systems in z, then you have a nice scaling that's independent of the frequency. Okay. And so if you write, first of all, in the pseudo-differential zone when z is small, then you have, again, this 1 over z, this Fuchsian term, and then this error term in gray is everything that has a better power, right? -1 plus some epsilon. Epsilon is usually 1 unless you have some non-smooth terms. And then in the hyperbolic zone, you have, again, this hyperbolic part, and then you have this Fuchsian part again, and then the remainder part now has power less than -1 because this is when z is large. Okay, and then from these equations, now one can also see that, why do you lose derivatives? Well, this comes from these terms in blue, this 1 over z terms, right? These Fuchsian terms, and the reason for this is something kind of very much from your undergraduate years, right? So if you want to treat these terms in blue, then what you would do is you would apply integrating factors, right? And these would basically, these integrating factors would be, because you have this 1 over z here, that there would be some power of z, right? And then this power of z then gives you powers of xi, and that's exactly what gives you the derivative loss. Okay. Okay, so at this point, we've done some rescaling, we've done some integrating factors, right? So these are all kind of very undergraduate level things, right? And then now the next question is, why is this not easy? Why is this difficult? Right? Why is this kind of not been completely done easily? Right, and so to just show why this is difficult, I can actually give an undergraduate reason why as well. And so we just look at what happens on the pseudo-differential zone, P here, right? And so kind of what you can do is you can diagonalize this leading order Fuchsian term here. And so then you get, as long as g of 0 is not exactly 1, then you get kind of this diagonal Fuchsian part. And then this remainder part is going to have a better power of z, so -1 plus epsilon, that's integrable. And then the unknown that's exactly what it is. It doesn't really matter. Okay. And so then if you want to get rid of this coefficient in blue, then what you do is you just apply the integrating factors, right? So basically z to the first power for the first component, and then z to the g0 power, right? And if you do this, then you then in the resulting equation for this transformed unknown, you exactly get rid of this blue coefficient here, and what's left is this part in red, right? So you have the remainder terms, except that the non-diagonal terms now have this power of z to the 1 minus g0 and then z to the g minus 1. Right? And so now the problem with this is that, even though if you look at, say, R12 and R21, those may be integrable, but then if you multiply by these new powers of z, then they may no longer be integrable, right? So this integrating factor could amplify your error terms so that they're no longer error terms. Okay, so then the idea, which is really the technical kind of heart of all of this, is that you want to diagonalize the system to higher orders, to even arbitrarily higher orders, right? And so then what you do is that you want to, say, renormalize the system to, say, nth order, right? And so this is actually, we did this independently, but then later on we found a simpler version of what we did in these papers that we're dealing with decay of hyperbolic systems. And so I think this is, so these things have been around for a bit. But the idea here is that we want to basically find a transformation, a linear transformation of the unknown. So we want to basically define this UPM, which is this matrix times UP. Okay, and then this matrix will just be the identity plus some expansion in positive powers of z. And then what's kind of a bit miraculous about this is that if you find the right transformation, then what you can do is that if you look at the system satisfied by this transformed quantity, then again you have this Fuchsian term in blue. But then what you can see is that the next m-1 terms in the expansion here will be diagonal. And then you don't reach any non-diagonal terms until you reach the nth step. And so this is just -1 plus n times epsilon. Right, and so then the point is that because what was preventing us from integrating this equation is this extra power here that could be large. Then, as long as you take this m to be kind of big enough so that you have a very large power of z, then you can absorb that amplification, and then what you can see is that what's remaining here will be integrable. Okay. And so because of this, then, as long as you apply the integrating factor to get rid of this part in blue, right? So then I can define basically this UA to be this quantity here on the pseudo differential zone. Then and then you can think of this as just an expansion involving positive powers of z, and then the unknowns, 1 over t times phi and dt phi, and then each branch has a different power of z from the integrating factor. Okay. And then this equation will now be uniformly bounded on ZP, this pseudo differential zone. Okay, and so now the observation here is that if you look at the ODE satisfied by this UA, then the coefficients are actually completely are integrable, right? This is so you can go back to just the usual ODE theory. And so what this means is that you can solve for this renormalized quantity basically from some positive time down to z equals 0 or t equals 0. And you can also do the opposite. You can also start from t equals 0, which is z equals 0, and then solve forward in time as well. Okay. And so right, and so that lets you get as good of estimates as you probably can. Right, and just a couple of remarks, right? So one remark here is that here I just wrote the expansions into powers of z, but I'm lying a little bit, right? So in some cases, these expansions can be polyhomogeneous, meaning that they can also contain powers of log z as well, right? In particular, if g of 0 is exactly 1, then your leading order Fuchsian part is no longer diagonalizable, right? So you have log z in leading order terms. And then also, if you have that g of 0 is an integer, then you can also have logs showing up in higher order terms in your expansion as well. Okay, so but the nice part about the proof that we do here is that we have an algorithm for computing this normalization expansions even with logs, right? And so this can be and so at least in theory you can plug this into Mathematica or whatever, and you can see exactly kind of the transformation you need to make for this all to work. Okay, so I'm using quite a bit of time, so maybe just speed up a little bit. So now on the hyperbolic zones, this is when z is large. We can also do a higher order diagonalization, but for various reasons, one has to do a very different scheme here than in a pseudo-differential zone, right? And so here, basically, what the idea is kind of the same. So you can diagonalize the leading order part of this equation, right? And the only difference is the leading order part is the hyperbolic part and not this Fuchsian part in blue. But the idea now is that from here you can find another transformation from this UH here to times some expansion, so that this new quantity here will satisfy a different ODE where again this part in orange is the same as before. This is only a phase, so it doesn't affect the size. And then this part in blue is Fuchsian, z to the -1 term is now a diagonal, and then also the next n-1 terms are also diagonal as well. And then you don't get anything that's non-diagonal until you have a very, very negative power of z. Okay? And that allows you to, again, absorb any error terms. And so then what you get is that, again, you have this quantity that's uniformly bounded in the hyperbolic zone, and then this can also be given as an expansion. Now, the only difference is that this expansion is now in negative powers of z instead of positive powers of z. And then if you're curious, these powers of z that show up in each branch is given by this thing here. But that's just what you happen to get. And again, this process for doing this renormalization is there's an algorithm for doing this, so we could plug this into a computer and have it done for you. Okay, and then in the intermediate zone when z is comparable to 1, then the analysis is trivial since derivatives really don't cause you any trouble at all. Okay, so we have skipped that part. Okay, so just putting that all together, so we had this renormalization in both this area where z is small and this other area where z is large, right? And so then if you kind of combine these two together, then what you get is this global quantity UA that's uniformly bounded, for all times and all frequencies. Okay? And again, this is obtained from a microlocal renormalization of the phi and its derivative. And then the theorem that we get for this model wave equation is that for this renormalized quantity, if you solve backwards in time, then it has a limit as t goes to 0, and then it's uniformly bounded. And you can also, given asymptotic data at 0, you can also solve forward in time, and so then this goes from t equals and then you again have a similar bound, of this quantity at a positive time by its data at t equals 0. Okay. And so one remark here is that if you look at this, this result in the estimates for this renormalized quantity, this u sub a, then there's actually no loss of regularity, right? And so I've been mentioning for the entire talk about this loss of regularity, and so where this loss of regularity comes from is actually that comes precisely from when you want to transform this renormalized quantity, this UA, back to the original, right? Then and you want to reverse that expansion, right? That's where you see this loss of regularity. Okay. And so this gives you kind of a new gauge where where you don't lose derivatives at all, and you have just a nice ODE. Okay, further extension, once again, this holds in higher dimensions as well by pretty much the same proof, very similar ideas, so I won't go into that. And then everything I mentioned before, we had this exponent L to be bigger than -1. And so in kind of an upcoming paper that we'll do, we can also get similar results when L is less than -1 as well. Right? And this is using the same methods, these microlocal zones and diagonalizations. The main difference is that the zones look quite different in this L is less than -1 setting, right? And the picture is here. You can, I guess, compare that to the previous picture if you still remember what that looks like. Okay. But that's upcoming work, so I won't say more about that. I just mention it here because I think I do want to mention some applications that are based on this as well. Okay, so next I want to talk about kind of applications, so some more generalizations of this and also applications. But let me just pause again and see if I have any questions. Okay, can everybody still hear me? Just out of curiosity. Okay, good.
We can hear you, yes.
Yeah, I always get scared of these things. Yeah.
It's the talk is a bit technical, but I am trying to continue to follow you.
Okay. Well, for everybody that fell asleep because that part was a bit technical,
Yes.
talk about applications here, so everyone can wake up again, at least for the last 5 minutes or so.
Okay, thank you.
Yeah, I'll skip the general theorem statement. I think I don't quite have enough time for that. So that's the super technical part. Okay, so what? Going back to the question of why do you want to do these kinds of results, or where could you find something like this? And so kind of one example, and this is the one that kind of motivated me, is mathematical relativity. And so these are wave equations on what are called Kästner spacetimes. And these Kästner spacetimes are basically common models of Big Bang singularities, and also some singularities inside black holes as well. All right, so here I won't get into kind of all the relativity, but the only thing you need to know is that the wave equation on Kästner spacetime, which is a bit of a linearization of a model for gravity, is given exactly by this equation that I have here. Okay, and so now it's basically it's very similar to the equations that we had before, but the only kind of new feature here is that it has this anisotropic hyperbolic part. So basically, in different components in the Laplacian, it comes with different powers of t. Okay, so now these equations have been studied quite a bit in the relativity community, and so it's well known that there are complicated asymptotics as t goes to 0, and there's also this loss of derivatives as t goes to 0, right? And so long story short, there's been many works on this, but I just do want to highlight a recent work of Warren Lee from a couple of years ago, right? And so basically what he did was that he identified the asymptotic quantities as t goes to 0, and in our language is given by what I write here, right? And so these are the quantities that have limits as t goes to 0, and they're also scattering data as well. Okay.
2 meses, pero los que tuvieron 2 meses tuvieron más visitas.
Someone switch off.
Yeah.
Don't worry. Yes.
Okay. Right, and then what they can show here is that you lose exactly half a derivative, as you go from positive time to the asymptotic quantity at t equals 0. Okay. And so basically, kind of what Warren did in his paper was he basically independently rediscovered these microlocal zones, right? And was able to adapt that to this anisotropic setting. But on the other hand, this wave equation here is simple enough that you don't have to renormalize anything. Okay. And so then what we're able to do is we can also is that we showed that they can also do renormalizations in this anisotropic setting as well. Okay. And so then what we can do, and again, there's not much physical motivation for this, is that we can extend Warren's result to kind of more general wave equations on Kästner, right? And so then what you see for these equations is that different components will lose different amounts of derivatives. Okay. More physical, something more physically motivated. So Warren's paper also treated the linearized Einstein scalar equations on Kastner. And so this is a hyperbolic elliptic system along with constraints and some gauge freedom. So I won't write the system here because it's quite long. But basically, kind of using the same methods, he was able to prove asymptotic and scattering results for a restricted class of Kastner exponents that are called subcritical. Okay. And so then what we were able to do in our work was to extend this result, right? So we want to be able to look at these linearized Einstein scalar equations for all exponents. Okay? And so for the subcritical ones, we can recover the same results that Warren had. But then for the non-subcritical exponents, then the new ingredient we have is this renormalization that I talked about. And then that allows us to get kind of estimates and asymptotics all the way to t equals 0, right? So we have to renormalize your equations in order to get the estimates that you want. Okay. So we can extend that estimate a little bit. Okay. A few other results. So also from relativity. So you have de Sitter spacetime, right? And so this is an Einstein vacuum spacetime with cosmological constants. I have the metric here, but let me not get into that. Right, and so this kind of has a very similar structure as a Kastner spacetime, right? And so there's a recent paper of Secordis also from 2024, and so he was able to derive asymptotics and scattering for the wave equation as t goes to infinity for this, and you have this basically a derivative loss by d derivatives where d is a dimension, and he also found the asymptotic quantities as well. And actually, this is part of a bigger program where he extended this to systems in the Einstein equations too. But that's a bit kind of beyond the scope here, right? And so this is kind of new, but not really new. So what we're able to do with our results is we can get a systematic treatment of the wave equation here. So if you kind of write this in the right coordinates, then the model equation that corresponds to de Sitter is this wave equation here, which we can treat using our methods. And so we can recover the existing results for de Sitter, as well as using our normalization, we can compute also the expansion for the solution up to whatever order that you want. Okay. Let me just quickly go through the remaining applications, and I'll kind of skip the general theorem statement. Okay, so maybe one other thing to mention is what about everything so far is looking at asymptotics and scattering as t goes to 0. And so then, what about when t goes to infinity, right? And so here I just write the Kastner wave equation, but we can do this for other wave equations as well, right? And so then there's a very undergraduate idea, which is just to replace, is to take as your new time to be just tau, which is 1 over t. Okay. And so if you make this transformation, then you get, in this case, the very similar wave equation, except that the exponents are now less than -1 instead of bigger than -1. Okay, and so then basically now this comes down to our upcoming results on for this L is it less than -1, and so in our upcoming results we'll be able to get kind of asymptotics and scattering for the Kastner spacetimes. And as whenever the exponents are the same, then there are already results for that, right? I think in that case you can actually write them in terms of Bessel functions, so you have something a lot simpler. Okay. Other applications, maybe I'll just mention the second one here, right? So this is just something that I found out quite recently, which is the 1D compressible Euler equations, right? And so there, I think many things you can say about that, but I think, but basically, here I'll refer to this paper of Chen and Floch from 2000, from the early 2000s, and so there they have these entropy solutions for general density pressure loss P, right? And so there the only thing I want to mention from that paper is that the key ingredient for constructing these solutions is to construct what's called the entropy kernel, right? And this kernel will actually satisfy a wave equation of this degenerate wave equation of our form here, with the exponent being less than -1, right? And so kind of again they did a full treatment of that in their paper, but here I guess using our methods we can also get an expansion for this kernel to any order as well. Okay. I think besides that, then I think the rest of this is just saying that we have a result for a general class of these systems that cover all the results from before, right? And since I'm already over time, I won't kind of cover what the assumptions are, but just say that we do have a theorem that covers a general theorem that covers everything that we discussed before, at least for L bigger than -1. The other cases kind of upcoming. Okay, so I'm over time, so maybe I'll just leave the future outlooks on the screen, and I'll thank you for your attention.
Okay, Eric, thank you very much for your interesting talk. We'll give now the opportunity to the audience if they want to ask some question or make some comment. Thank you, Fabrizio. Oh, someone has the micro open. Maybe in the chat. Someone has it's a micro open there, but okay. Meanwhile, I would like to thank you, Eric, for your clear, organized talk. Very technical.
Was it clear? Yeah, sorry about that.
Yes, don't worry. But it seems that the topic is like that, no? With many details, no? And it's not easy to study that. Yes.
Yeah.
It has been interesting. And I had one curiosity, maybe you have said, but I haven't understood.
Okay.
Because you were when you introduced the model, the model on page 9, I think that in the slide 9.
9, okay.
Yes, you said that the on page number 9.
Yes. Yes.
Yes, you said that in that model, the loss of regularity does not depend on G and H, no?
Yes, that's
Yes.
true. Yeah.
And then on page 12, when you introduce another model, I don't know
Yes.
for that case if the result of loss regularity depend on G.
It does, right? And that's
Yes.
because we have this extra t to the
Yeah.
-1 here.
Yes,
Right?
I thought that
Yeah.
because that term could, yes.
Yeah. So in this general case, the loss of regularity is going to depend on L, on A, B, C, G, and H.
Yes.
So yeah. So it's I think I have these powers exactly because this is the exact power you need to have kind of loss of derivatives depend on the coefficients.
Yes, interesting.
Yeah.
And then when you were introducing this type of models, I was thinking by myself, where are the application or where this type of models come from? But then at the end of the talk, you explained some of them.
Yeah.
And
Okay.
yes, you told I have no idea about general relativity and those topics, but you mentioned one space-time that I don't know, maybe it's difficult to explain, but the Kastner space-time, I don't know.
Yes.
What is that? Do you know? It can be simply explained, or maybe
Yeah,
not.
so it's a space-time that people study in cosmology. So I think if you look at I think it's one of the simplest models of the Big Bang singularity, right? So what happens at the beginning of the universe, right? And so that's I think that's one kind of a simple model background for this Big Bang singularity. That's where people see it. But you also see special cases, I think, but it's also quite generic. I think if you look, say, inside the Schwarzschild black hole, right? Then kind of what happens, what at some point inside the black hole, you also have a singularity, right? Your curvature that goes to infinity, right? So there it also looks like a Kastner space-time, right? So I think that comes up quite a bit in kind of various settings.
So it seems that there are many applications in general relativity topics, no?
Yeah.
Yes.
I think they're also if you're more of a PDE person, right? So I think if you look at let me go to the end. If you look at say nonlinear wave equations, so box of phi is equal to b phi to some power, phi to the p, right? So then there are these ODE blow-up solutions, right? Phi is t to some power, right? And so if you linearize your nonlinear wave equation around the ODE solution, then it also looks like this. It has this structure as well.
Yes.
Right. And so that's it. Yeah. It comes up quite a bit.
Mhm.
Right, and
Yes, thank you, Eric.
mhm.
Is there any question in the audience?
Excuse me, I would
Yes,
like to know if it's possible to obtain numerical solution for these problems.
Uh, I think so. So I mean, this is something I want to explore with people in numerics, right? So I think in general, if you look at this, say Kastner as a simple example, right? Where we go? Right. So now, if you were to try to do numerics for something like this directly, right, then because you have these powers of t and some are going to zero, some are going to infinity, then it's very, very difficult to do numerics, right? And so then what you can, I'm sure people do this all the time, but it's just hard to go to a t equals zero, right? And so, I think it'd be interesting if you can, try to take these renormalizations that we do, because these things are, perfectly bounded quantities, right? Then to kind of do numerics for that instead, right? And in the
Excuse
Fourier
me,
space. Yeah.
excuse me, Professor Arick Shao,
Yep.
but the problem of the black hole, generally, the equation is the quartic order, huh? An harmonic quartic order.
For the are you talking about the Einstein equations or
Because I see some
yeah,
equation, the
yeah.
quartic and
I
harmonic.
mean, yeah. The Einstein equations are usually quadratic, second order. I think there are some modified. If you change the gravity equation, that people explore alternative PDEs for gravity, and those can be formulated as quartic equations. But I think Einstein, if you look at just the usual gravity equations, those are quadratic.
Yeah, another question. I would like to know if you work about the vibrational problem of DNA denaturation, like a Peyra-Bichot equation.
The what equation, sorry?
Peyra, the model of the vibrational equation for the DNA, for DNA, for the biomolecular DNA, in the case of biomolecules.
I'm not sure what that is.
The model, the Peyra-Bichot model.
Yeah, you sure? I don't know. I haven't seen it. But you have a reference for it. I'm happy to take a look.
It's a hyperbolic equation.
Okay. Does it have this kind of structure as well, or because that would be interesting to find even more applications.
For biological, do you have some biological application?
So far, no. I guess I mean I think these things will be relevant to some fluid equations as well. So if that connects to biological, then maybe. But right now, I don't have any in mind.
Some question. What is the prediction for that equation about the black hole, for example? What's the implication in the in the university problem or in the cosmological problems or astrophysics? What's the impact of that equation?
I mean, okay, so the wave equation here is just a linear model for the Einstein equations, right? Which is a very nonlinear equation, right? So people have studied, what happens, for the nonlinear Einstein equations as you go to the black hole, like something close to Kastner, right? And so people kind of know, basically, kind of what you get is the behavior is basically the same kind of behavior that I talk about here, except you have a different exponent, you have a different loss at every point, right? And so you have so I think what I'm mentioning here is kind of what you expect to see
Another
for
question, Professor Arick Shao.
yeah.
Is possible to insert electrical transport equation or charge transport in this equation?
Probably. Yeah, I mean, I think, I said, this is more like a framework for treating, this kind of structure, right? And so, as long as you have this kind of a hyperbolic equation with the structure, then plus other things, then you can do that, right? So I think one thing we do is linearized Einstein equations on Kastner. right? And so there, it's not quite a hyperbolic equation, right? It's a hyperbolic equation plus elliptic equation, and it only has that structure after you do the right gauge transformations, right? And so then you have to kind of mix the tools we have here with kind of tools from other parts of PDEs in order for this to work. But you can do that, right? And so one can kind of consider, you know, something like this coupled to other kinds of equations, other terms as well. Right, but it would depend on the model.
Because in the cosmological problems, there is additional equation, like a fermionic equation, the charge transport, the complement for this equation.
Okay, that I'm less familiar with. I think I've done more kind of classical relativity than
A fermionic, like a fermionic electrical equation, not only a spatial equation, but it's necessary to analyze with the electrical charge transport in the space.
Yeah, okay, that's I have to look at the equation. Okay, I'm not as familiar with that equation as I am with kind of the wave and the Einstein.
Okay, Professor Arick Shao. Thank you very much, Professor. Thank you very much.
Thank you. Thanks for the questions.
Yes. Thank you to all of you for the questions. So I think that we will finish here. And before saying goodbye, I would like to announce the next seminar speakers. We will have the next seminar in 2 weeks.